corona is with 3.25 million deaths per year worldwide. And if we contrast these numbers with sepsis, we see even higher mortality with 11 million deaths per year worldwide. Estimated that 20% of all deaths worldwide are associated with sepsis. And I think most of you know that that's the disease that need a very rapid and intensive medical treatment. So if you look to the numbers, it was clear sepsis need to be taken serious. So how does sepsis develop? Sepsis normally begins with a local site of inflammation, and the majority of the case, the body can stop the inflammation by its own, contain it locally, and resolve the problem. But if this is not the case, then in the second step, the pathogens enter the bloodstream, spread throughout the body, and finally, this leads to damage of vessels, tissue, and organs, and in the worst case scenario, to multi-organ failure and to the death. The aim is to stop this circle at the beginning. But regarding to this context, there's on the one hand the medical treatment a problem and the mechanism of action. Usually, the application of drugs is systemic. This means that we inject, for example, drugs, and they distribute in the whole body. And it's the site of implementation. If we give them a special concentration, the concentration is not high enough to stop the problem. But we cannot give a very high concentration, because then outside of the implementation in the rest of the body, very strong side effects follow. And this is a very central dilemma. So the target is to find the right dose in the middle. But even then, damage of healthy tissue follow. So to solve the problem, the target dosage is the aim. And therefore, one solution includes a target drug delivery. And therefore, we can use, for example, nanocarriers. Nanocarriers are shell, and they work like a cap with GPS. They transport the medically active ingredient to the infection in the body. And for this purpose, it is important that they are tailor-made. And on the one hand, it is important that they encapsulate very different active ingredients, because we have so many different active illnesses, and so we need so different active ingredients. And on the other hand, the desired release is needed. In addition, the loaded nanocarriers should circulate undetected in the immune system in the body as long as possible. And also regarding the requirement of the nanocarriers, the release only takes place at the desired target site, the site of implementation, through selected stimulus. And selected stimulus are, for example, the pH value, proteins, biomarkers. If we think to tumor cells, and as an example, tumor cells has a very acid pH value, more acid than the rest of the cells. And so by this pH change, the nanocarriers can encapsulate the active ingredient only there. And so we get there a high concentration and not in the rest of the body. And all the requirements I mentioned are fulfilled by polymers. And so we can say polymers are ideal starting materials for nanocarriers. Here you can see a research group in a collaborative research center of polytarget. Their research work for target drug delivery in different fields of science. For example, in chemistry, medicine, material science, pharmacy, and biochemistry. And we, as a didactic group, are also part of it. And it is our aim to transfer this actual topic for school and make it possible that the students are participate in the development process. And regarding to this, there's a question, what is the potential of nanomedicine for chemistry education? How can we transfer the topic and should it be? In our opinion, there are different opportunities for chemistry education. On the one hand, there's the live-work connection. The students mostly are all contact with medication and side effects. And not least, the corona pandemic touched the everyday life of all students. By corona, it is also not the virus themselves cause the problem, it's more the immune reaction. And so we have the nearly same starting point like in sepsis, even when the central topic of polytarget is not corona, it's sepsis. In terms of content, there are different connections to classical topics of chemistry education. For example, polymers, polarity, ester formation, ester cleavage, and so on. The topic also gives the opportunity for interdisciplinary teaching and research contact by the topic of medicine to the subject of biology. And to the motivation subject area, there's a study who shows that 87% of the asked students show interesting factor to nano in general, and we know from all the studies that especially young women are interested to medical topics. Since the amendment of the educational standards in 2020, nanoscience education was integrated into the standards, and this leads to the implementation into the curricula. But up to this point, there were no experiments to the topic of nanomedicine to drug delivery. And so it was our goal, or it is our goal, to change this. But of course, there are different barriers. If we think to the research, if the researcher wants formulate drug delivery systems, they take active ingredients, they take polymers, mostly adaptive with so-called stealth proteins, and then different research steps follow. They need special equipment, they make analytics, purification, and so on. All steps we can, of course, not carrying out in the school context. And if we look to the teacher, they also see barriers and hurdles for the actual topic. So, for example, they say, how can I teach the current interdisciplinary research in my classroom? I can't carry out the experiments with the equipment and chemicals at my school. You see a lot of barriers. And it was our aim to take the barriers from the research as well from the teachers and to a ground of our basic to the development of the test series. And now I would like to present the test series we developed up to now. In the first test series, it is divided into 3 parts. Students can follow all steps from the synthesis of the polyesters, the preparation of the nanoparticles, over the nanoprecipitation and loading, to the final part, the degradation and the release. In the first part, the preparation of the nanoparticles is focused. Therefore, a synthesis of a polyester is carried out. We decide for the polymer polydata-valerolactone. And therefore, the students can carry out a ring opening polymerization of the monomer data-valerolactone. For a very fast reaction, we take the organocatalyst TBD, triazocyclodecane, and as the initiator, we choose ethanol. The experiment takes 10 minutes, so it is possible in terms of a school lesson. And like you can see in the pictures, the students can follow the reaction with the next eyes. After the synthesis of the polymer, they take their own synthesizes polymer for the next step, for nanoprecipitation. For the nanoprecipitation, they use the polymer and dissolve it in the solvent. It is important that the solvent is mixable with water. If we want loading the particles with a dye, so we choose nyrate, dye were also dissolved in the same solvent, acetone. After this, the organic phase with the polymer and the nyrate taken and added into water. Then on a stirring plate, the acetone evaporates and the nanoparticles are formulated. So these processes are based on the different polarities. By using the co-precipitation for the formulation of the particles, it is a very simple method for the school. And instead of it is so simple for the students, we can formulate nanoparticles in the desired range up to 300 nanometers. Here you can see the process of the injection of the organic phase into water. For this clip, we use a micro pipette, but it is also possible with a simple Pasteur pipette. The end of the particle solution you can see on the white picture. There is on the one hand under normal light conditions, and on the other hand under ultraviolet light. In the last step, there's a focus on the degradation of the nanoparticles and the release. And for the school context, we decided for a very simple method by a pH value change. Students can add sodium hydroxide solution to the particle suspension, and then the degradation follows. Of course, it is possible to use other stimulus than the pH value. For example, temperature change, light, ultrasound, enzymes, or magnetic electric field, and so on. Why did we decide for a pH change? On the one hand, it is very simple to use it in the school context, and there's a connection to the subject of biology. The students know from biology that we have in the human body different organs with different pH value, and so we can take this knowledge and transfer it to our experiment. By adding sodium hydroxide solution to the particle suspension, the degradation of the nanoparticles and the follow and the nyrate release. You can see it by the next eyes on the picture. And this reaction after added sodium hydroxide solution, the simple alkaline ester produces under a new context. And for a successful implementation in the school context, the costs are also very important. And for the experiment series I presented, if we carry out this series in a class group with 8 groups, so 16 students, it costs 6.55 euros, so it is comparatively low. And now, if you are interested in more analytics we also made in the development phase, or more, what we also tested, you can look to our paper in the Journal of Chemical Education, or of course you can contact me or ask after the presentation. So, and this was the first experiment series with the methods of nanoprecipitation. In the next step, we developed a test series where the students can formulate nanoparticles by the method of dialysis. Therefore, they also solve a polymer. Here we use a cellulose derivative, cellulose acetate, and they dissolved it in solvent. We decided for DMSO and dimethyl sulfoxide. In the research context, they have often used DMA, dimethyl acetamide, but it is not allowed for the school context. And so we made a simplification that it is possible to transfer to the school. After the organic phase is added into the dialysis tube and then put it into water. Normally, in the research context, the water change all 20 minutes for 15 hours follows. Of course, this is not possible in the school context. But we tested, and it is also possible with no water change, and after 20 minutes we can see visible results. By checking if there are nanoparticles or not, we can use no analytics in the school. But it is possible to use the laser pointer and test with the Tünder effect if there are nanoparticles or not. Of course, we can also use the Tünder effect for the other test series. And for the both test series, we started to evaluate with different student groups. So we integrated the test series in our student teachers lab. We sent materials to Genua, and they also carry out the experiment. Last year there was a student lab to the topic of nanomedicine. Every year in Jena there's a nano summer school, and there also the students carry out the experiments and evaluated the results. And in February of this year, there was a teacher training course. The teacher carry out the experiments by themselves. They give us feedback, and we try to make the experiments more better based on these feedback. First insights of the evaluation shows us that the interest of the learners in the subject is there. Therefore, we use on the one hand the oral and the written feedback from the teachers and the students, and we have developed a questionnaire in a so-called pre-post design. 78% of the students rate their own knowledge of nanomedicine better after the test series and the sequences than before. And in addition, the learners emphasize the clarity of the experiment and especially the viral effects. If we compare the pre and the post test, then it becomes clear. And while in the pre test, the concepts and the knowledge is non-specific, it's more general. In the post test, 76% of the learners can concretely describe drug delivery, the process of drug delivery by nanocarriers, and finally the release by specific stimuli. And this brings me to the end of my presentation. Thank you for your attention. And now, if there are any questions, please let me know.